Good afternoon, everyone. I'm Sina, a PhD student at the University of Sheffield, and I'm happy today to present our work, Missing-Modality-Aware Graph Neural Networks for Cancer Classification. Actually, as we know that cancer is one of the most life-threatening diseases in the world, and it's driven by many different omics modalities. It can be a genomics, it can be proteomics, it can be transcriptomic, and even more. And as we expected, multi-omics integration is expected to provide a more comprehensive overview of the patient's profile that can help us to understand the problem better. But always when we talk about integration, there are a couple of issues. One of the big challenges is about the missing modality problem. That actually, yes, we don't have information for all the patients. We have information for some modalities, but actually not for all modalities. So in this case, we have a missing modality. But the main problem is that missingness can happen anywhere. It can be in the training set, it can be in the test set, it can be like a missing one modality, we can have a missing two modalities, and it can like a diverse missing modality patterns that we have for data set. And another thing is about the evaluation itself, that sometimes people only do like a simulation for the missingness that can be considered like a kind of data leakage. They assume, for example, one specific modality is missing. But actually, in the real world, we don't have that kind of information. Missingness can happen anywhere, in any modality for any patient. So with having this issue in mind, we are going to propose an architecture, magnet, that is going to handle it. Just imagine we have three modalities here. We first have a simple encoder just to have a same representation dimension for each patient in different modalities. And the main thing is about the attention mechanism, that we try to calculate the importance of each modality for each patient. And if it's one modality missing, we try to mask out those modalities from our calculation. And then we have a weight for each modality for each patient that we can try to build a complete data set. It's not an imputation. We just try to assign a weight and try to learn from the missingness. And based on this, we try to build a graph that nodes indicate the patients. And for building the edge, we try to consider the original data itself. And if two patients have one modality in common, we consider that edge. If not, we ignore that edge. And then we have a traditional graph neural network to learn from this graph. For evaluation, we considered three different data sets. And the problem is that, and the main important thing here is that we have considered many different patterns that is, as I said, is originally available in the data set. And yes, Magnet got a better performance compared to the state-of-the-art methods for the cancer classification. And if we just look at the representation learning, we can see sometimes a mRNA here, it's like a dominant modality here, but still for some of the patients, it's for the breast cancer that we have 5 types of a classification. And we can see that for some of the classes, they are coupled to each other, then they are not separated, but our model tries to separate even those specific types of a cancer from each other. And if I go back to the main model, the main important thing is about this model is about the linear scalability when we have a more modality. And another thing is about the generalizability. This model, although it's designed for the cancer, but it can be used for any other topics you have until you can until you have an encoder for your modality. That's it. Thank you.